we have started. I see. So I will list the problems that I believe okay. There's the infinite. I'm going to say square well, which is what I was calling it in the book. They call it the quantum well. That doesn't. They're all quantum wells. So anyway, it's the one that looks like this, right?
Mm-hmm.
Oh, sorry, that's the wrong. Hard to shade in. So this is the x-axis, and this is the energy. So it's I'll use this as the x equals 0 then. This is A or whatever, or L, I guess. And this is well, it's really well, I'll say V, yeah. It's just energy, obviously, but sorry, I'm distracted by this. So these are the reason I'm showing this is because it's infinitely tall, right? But this is the one problem. The other one we do is I'll call it finite barrier. Really, it's tunneling. Tunneling. I don't know how to spell.
It's okay. I just thought the same thing.
I think there's 2 N's and 2 L's.
There's not 2 L's.
There's not 2 L's.
You sure?
No.
Okay.
No, because
It looks better with 2 L's.
there definitely is not 2 L's.
All in on 2. Go ahead. Okay.
No, maybe not.
No, I like it better with 2. Let's just say that because it looks like a tunnel. That's not how spelling works, but anyway.
I like that. Okay.
So infinite square well, finite barrier,
I'm definitely wrong, but okay.
and then, which is like this. This is the same. This is the potential.
You're right.
There's 1 L?
There's 2. You're right.
Oh, there's 2, okay.
See, this is why I don't offer my opinion often.
And this is X. And tunneling, yeah, okay. This is called like, maybe bound state, you could call it. Okay. These are all actually what they're called. I don't know how much he's introduced any of these words. From what I can tell, he's not. But this is like a bound state, meaning that it's like a fixed stationary state.
Mm-hmm.
I don't know. Basically, there's fixed energy levels. So remember when he was showing you all the. So yesterday was okay. It was a good. Like he showed a bunch of stuff.
You
And
sound so surprised.
no, but it was like he was showing all the. So he was showing the square well.
Mm-hmm.
So here, let me just run over this real quick because there was a part that he talked about for a while that I kind of want to emphasize more. That if you have a square well, if you plot the energies, there's like. This or whatever, I don't know. And it's like that. Right? These are the bounds. So this is energy. And you could call this like negative V and this 0 if you want. It doesn't matter. Just like with MGH, remember with potential energy, it doesn't matter what we call 0 because you can just shift everything and it's still fine. But let's say this is a negative energy and this is 0 energy. If you solve it, and solving it means solving a potential, solving a quantum mechanics problem means finding the allowed energies, right? And or the wave functions. And the reason I wrote n is because there's like integer numbers of them.
Mm-hmm.
In this case, it's actually not like the solution is like e to the I kx.
You're in the right place, Joe.
K is not.
Joe.
Jeez.
Just ran right into Joe. I'm so sorry. I was like, I'm gonna be so smooth and just slide back.
That was awesome.
I'm never
I think you can leave.
How do I want to say this? So remember for the scattering. Sorry, it is called scattering, but I don't want to say that because you haven't heard that before. Tunneling. For the tunneling problems, remember the incoming one has just K, and that was actually like radical 2me over h bar. Remember when we solved the Schrodinger equation? So whatever, but this does not have to be an integer. So this is not quantized. Right, this thing here is not quantized. Now, technically, everything is quantized in quantum mechanics, but we didn't get it quantized from the problem itself. Right, the energy, as far as we know, K could be kind of whatever. So solving a potential, like solving a bound state problem would be finding the energies and the wave functions. In this case, the energies are sort of arbitrary. We don't actually find, because it could be, like I said, it could be whatever. But we do have to find the wave function, because that's what tunneling means, is that the wave function is sort of, if it was 0 everywhere over here, there would be no tunneling. The fact that it's not 0 everywhere on the right side, if it's coming in here, means that there is tunneling. So somehow we're finding these two things. If it's a bound state, we can always find the energies, the allowed energies. Allowed energies. And this is kind of the big thing. This is the big new thing. So, I mean, you've seen, like, okay, I'm trying to say it. Okay, so remember before when we solved like the setup of the string, of the guitar string, and we found the modes, it can only vibrate in these certain standing waves, right? That's actually a quantum solution. It's quantum because there's quantized things. It's not like you can't just put any function you want, psi, on there, right? You can't just say, I have a guitar string and I want to vibrate it, and I want to go like this and then kind of stop and then go like this. It doesn't, that's impossible. This we found because it has a differential equation. The solutions look like that's the first one, and then this is the n equals 2, and then we get n equals 3, right? That's literally the exact same thing we're doing here. But of course, in the Schrodinger equation, one of the terms that we get, it's just like in the string equation we had what do we have? MA and F equals MA equals KX, or that was like the spring. But anyway, we had some numbers and stuff. But in the Schrodinger equation, we actually have energies, and I'll write it. So this is the thing. So if you've seen the longer version, he sometimes writes, which is the full Schrodinger equation, where this side has a time derivative. But anyway, I don't think we're going to do that ever. I don't think it's even in the book. So anyway, but this is just the fixed energies. This means that this only works if your state is a stationary state. Stationary means there's no time derivatives anywhere in here. Nothing is a function of time, which is fine because you can actually do most of interesting quantum mechanics with bound states, bound or stationary states. So that's why there's no time anywhere in here, and that's why psi is not a function of time. In general, of course, it can be a function of time, but it's not. And in fact, in this case, it's only a function of x. And I'll talk about, I don't want to forget to talk about this, talk about 3D Schrodinger equation. I'll talk about that at the end because he mentioned it in class and because I know the next chapter of the book is about it. I don't think you'll have to actually solve many things with it. Well, anyway, we'll see. Okay, so just like with the string, it's not like any function that I draw psi of x can solve this. This is a very specific thing. This says that if I take two derivatives of a function, it gives me a number times that same function. So we saw last time that when we put it in this box, we only got like sine functions and sine n, what's like n pi. Like we got all the things with the quantization, just like exactly the same as with the string. And we got that only certain functions like sine can satisfy this. We can kind of see already that sine is going to satisfy it because two derivatives of sine is minus some function, like some number times sine itself, right? That's how we knew how to solve this originally when we did it with classical mechanics. But anyway, so the whole point of all these is to go from the potential to the allowed energies and wave functions. Now, usually we find these first because that looks like you're going to solve the wave function, right? That's kind of what it looks like. So last time we solved this for the infinite square well, and then when you plug the solution back in here, you can actually solve exactly for the energies. So we found this by, differential equation solving, right? We literally did this last time, but it's kind of just like plugging in. So plug in psi equals, I'm I mean, you could do a e to the I kx plus b e to the minus I kx, which is a. It's not actually the same a, but whatever. So remember all these techniques we did about plugging in example solutions to these types of problems? It's the same exact thing. We solve it. We get a psi of n. The word you might think, okay, I don't know for sure that it's n, but where does the n come from? Well, it comes from when I set it to 0 at the boundary conditions. So then we use boundary conditions. Boundary conditions gives you psi of n equals something. It's like sine of n pi x over L or whatever it is, right? So, so that's how we get those. Then we plug back in psi n here, and we find En. And remember, En for this square well was like, we got En equals, like n squared, pi squared, I forgot what the rest is, something squared over, h bar squared over 2m a squared?
Yeah.
Yeah, so that's what we got. So this is not obvious, and you almost can't do this without solving the psi first. Anyway, so this is the solution, and now the reason that he was showing that is that because if you actually plug those in for some potential like this, you can actually show where they are, and these are where the allowed energies are. And what that means is that if you try to put an electron in with, like if you put a particle in here, it's just like atomic orbitals, right? You can't just take a nucleus and just put an electron anywhere you want in it. There doesn't exist a state that that's stable in. You need to put it in certain places. There's 2 orbitals you can put it in at the closest shell or whatever. Something about shells, I don't know chemistry, but anyway, you know what I mean. There's only allowed states. This is identical, but this is actually simpler because it's a square well and not an atom. That's a little more complex. It's spherical, but anyway, so they're showing the allowed energy states, which in other words means allowed numbers here. So again, like I said, not every function you could just name will solve this equation ever for any values of anything. Not every function, take tangent of x. The second derivative of tangent of x is not proportional to tangent of x. So that'll never, ever, ever solve this equation. So tangent will never describe a wave function of a particle in this box. So again, the whole point of this is to find the solutions, but in the same way, this is a new thing now to quantum mechanics, not every number is possible either. You can't always just find a function where some number you make up solves this. There's only specific functions, and they come with specific numbers, and they're labeled by n. They go together, of course. So the psi 1 has energy E1, and psi 2 has energy E2. And so we get that the solutions have these n's in them. And and that's what quantized means, because you can't just slide it up and down like a scale. You have to have specific values. And that comes out of the boundary conditions. Again, we didn't know from this function that it would come out to be something with integers. We thought, it could just be, I don't know what's going to happen. It could be anything. E is just a real number. That's all we know about. But it turns out that for solutions of this, given the potential, sorry, I forgot the potential. Anyway, V is the potential. It's just E minus V. It's like the extra energy kind of thing. Anyway, this would be a free particle if I left that there. Because of the potential, we find that only certain real numbers here can satisfy this, and they're labeled, and you can plot them, and it kind of, actually, this might not be, well, I don't know if this is to scale. Anyway, it doesn't matter. The point is that there's a ground state, which is the lowest energy state, and then there's excited states, which are high energy states. And for different potentials, solving this is easier or harder, whatever, but with the point of him showing that little demonstration, the online thing, whatever it was, is because if you do a different potential like this one, this is the Coulomb potential. Coulomb means that the potential U, I'll say V now. U and V are always going to be the same thing for here. V is 1 over R, right? So remember, if V is 1 over R, that means that the force is like 1 over R squared. This is like electric fields and gravity when you're really far away and stuff. So these mean the same thing, because this is the derivative of the other one. Anyway, so V is 1 over R. If you just plot 1 over R, it looks like this, right? Like absolute value of 1 over R. And you get that the values of energy, so this is, of course, still energy, potential here, then the values you get, the lowest one you get is like here, and then you get here, and here, and here. And now, this is literally a hydrogen atom. A hydrogen atom has a single proton, and the electron feels an attraction just like this. This is just electric attraction, right, between negative and positive charged particles. And assuming you say that the proton is fixed, then you can say, what does the electron feel? It feels this potential just like this. And therefore, what are the allowed energies it can have? And you get just certain values like this. And these are the n equals 1 shell of the electron, the n equals 2 shell, etc. Now, this is one-dimensional still. I should mention that. This is still one dimension. So, of course, real electrons are three-dimensional. But, real hydrogen atoms are three-dimensional. But this is the one-dimensional version. So you only get, you can put one electron here and one here. Well, you could put two because of the Pauli exclusion, but we're not going to talk about that. So anyway, and then given another one, if I draw, what else did he do? He did the harmonic oscillator. The harmonic oscillator is, oh, fantastic. The quantum harmonic oscillator is so good, but it's not in the book anywhere, so I'm not going to, I'll draw it, but I'm not going to, we don't have to derive it. But I'm really surprised. He should honestly cancel anything to do with quantum dots, which I don't even know what that is. He should cancel all that and do the quantum harmonic oscillator because it's so much better, because it looks like this. So the potential is like x squared, right? Now, because remember, with the square well, it was like 0 and then it was infinity. It was kind of a weird thing. With the Coulomb thing, it had a nice function, like it was 1 over r, but it still looks a little weird. There was like an infinity in it, right? This is a very normal looking, like this is like a classical mechanics problem. X squared for your, like a roller coaster on x squared. Find the potential energy. Like it seems like something you would do, and it turns out, and so of course, there's ways you could write it here. Anyway, I won't get into it, but there's ways you could write it here, and when you find the energies, they actually are evenly spaced, which is really cool. And then this is the ground state, which is not at 0. And then you could compute these combinations of different things in here called raising and lowering operators, or ladder operators. So you get a quantum state called the ground state, and you could say, if I act on it with this raising operator, I get the first excited state, and I act on it with another raising operator, I get the next one. And if I use a lowering operator, I get this one. Anyway, and that's really cool because that's like a new mathematics that comes out of just rearranging things. Like it's not like a new concept. It's just rearranging some numbers in here when you plug this in. Because of the squared and the way you can solve this differential equation, you can actually compute this sort of new formalism for describing a quantum harmonic oscillator. And then you spend, in a quantum mechanics class, you'd spend 2 months or so just doing this problem. Which is actually kind of interesting because you do different things. But apparently, in this class, we're not going to do it. So I won't talk about it anymore. Anyway, but the point is that given any potential, you have to do the work of solving this equation to find the allowed energy levels. That's the whole new thing of quantum mechanics. It's not like they just tell you that there's this much energy and then you convert it to kinetic energy and you can convert half of it back to potential. You can't do that stuff. With the hydrogen atom, again, here's the energy, the allowed energy levels that you'd solve for. If you give the atom a little bit of energy here to go up to like it has, if you give it this much energy to go from here to here, it will just not do anything. The electron will not absorb that. If you send a photon to it, the electron's sitting here, if you send a photon to it that has this much energy, it will just pass right through. It physically will not interact. If you send a photon with this much energy, then it could absorb and jump to this level. But you cannot give it this much. I mean, you can, and it won't do anything because there's no allowed energy state here. It doesn't satisfy. There is no wave function it could have that would satisfy the Schrodinger equation. Does that make sense? So that's the main point, I think, of everything when he was showing this with the lines on it. I think that's the whole point he was trying to get across, is that that's the new thing in quantum mechanics, is that it's not just like now we have a differential equation that describes strings or something, and we can use those to like find some functions. It literally says that the particles that exist have to be ones by sort of construction that obey this equation. And there isn't, if the energy is this, I'll call it E1, which is not a solution to this, if you plug in V equals 1 over R, if you plug this in, E1 will never solve this equation. Therefore, it's impossible to have an electron with that much energy in this system. If you tried to put one in, you would just like fly away or whatever. It wouldn't, there'd be no, or it would drop down to here and emit a photon with this much energy. Unless there was an electron already in this state, in which case it could not occupy that because of the Pauli exclusion principle, which just says that for electrons and things with spin half, which is like electrons and most like matter, you can't have things in the same state. But that's a whole other thing. Anyway. Okay, does that make sense? Like, do you see the point of these diagrams now that he was saying in class? Did he say, okay, let me ask you, did he say anything in class about this that you're still confused about? Confused beyond the, like, maybe you have to think about it for a while, which is fine, but like, he said something that you were like, I don't know what you mean. Okay. All right, so okay, so I'll move on. So this was, and I'll talk about tunneling real quick. And again, and that's sort of, I talked about it last time, but I didn't give a good like qualitative overview. And then we'll do a finite well, which is, I believe, it might be on the next homework. It was in the book in like the next chapter, so I'll do it. Okay, so then oh, and I have to do the 3D one too. I'll talk about that in a second. So for the finite barrier, we had a free particle coming in. A free particle is one that satisfies this Schrodinger equation with V equals 0. We know the solutions to that because we know how to, where do we use that? For waves and stuff, we use that, right? And so that would just be like this. And of course, there's another term for it going the other direction, but we can just pretend that it only goes in one direction because we only care about the tunneling this way. So we know it goes like this. Now, on the other side, so in region 1, so I'll go through this real quick. I'm not going to go through all the math, but I am going to go through it in a way I think is better than I went through it last time, which is why I'm doing it again. So in regions 1 and 3, so psi 1, psi 3. So remember what I said is we have a potential. Here's the potential. It looks like this. It has a height of V naught. This bottom part is at 0, and it has a length of A. And it's a finite barrier. Finite, because if it was an infinite barrier, it would be really boring. It would just stop here. And there would be 0. The wave function would go to 0 because you can't go through an infinite barrier. But to find this, remember I said the point is to take the potential and find the wave function. Now, if there's 3 regions with 3 very different things happening, we can just break it up. Now, of course, if we solve all 3 of these, then we're done because we just have that's the wave function everywhere. We don't have to be able to write it as one thing. Maybe it looks different. Now in region 1, we have this, as I said many times. This is the solution. So it looks like A, e to the I k x, and again we of course get B for the thing going the other direction, but we can just consider. Let's just talk about something going to the right because tunneling we care about this way. Okay. So that's the solution. Now let's actually skip to 3 first. Now 3 is identical to 1, right? There's literally no, it's the same Schrodinger equation, right? Yeah, everything's the same. So it's literally going to be the same, but of course, we can't use the same coefficient because we don't know any number A will still solve it because the A's will cancel if we plug it in. So we don't necessarily know that the magnitude is the same, but the form looks exactly the same. It's still going to the right. So as K. Remember, by the way, K, I used K as a substitution. K is actually square root of 2me over h bar squared. That's actually what K is. You could take the h bar squared out if you'd like. I'm just using K because the book uses it, and it just makes the writing the exponential is a little easier. Now what about region 2? Now we still, okay, maybe we've solved it, but we still, it's weird that we have 2 random constants. Maybe we could simplify this. In region 2, well, the potential is V naught, right? So let's write the Schrodinger equation again. equals, and now I'm going to write it as E minus V naught psi. And this is the thing where, well, remember E, and so, oh, sorry, I should mention, I'm assuming that E is less than V naught. The energy of the particle is less than V naught. If it was greater than V naught, we could still do it, but it would be slightly different. It would be a little too easy. But because E is less than V naught, this number here is negative, so I made a big deal about this last time, how this number is negative now. Negative. Okay, so what I want to do is make it positive so that if I need to take any square roots, which is kind of a hint, then I don't want to worry about i's and square roots, right? So if I take a square root of something, I want it to be a positive number. Actually, I did that last time. Let me do it a slightly different way this time, but it's going to give us obviously the same answer. So we know that this differential equation, if we move everything over, we get d squared dx squared psi equals 2m, so it's minus because of this minus sign here, E minus V naught. I'm not worrying about the fact that it's negative right now. Okay, so everything's fine with this. This is just moving things over. Now we get this. Now this looks exactly like how we got this solution, except that instead of k being this, we have k is, so literally the solution is c, I guess, it's a new variable, e to the I k prime x, because k prime is now this thing, which is 2m e minus v naught over h bar squared. Does everyone follow that? So it's identical to the solution to the other one. The minus sign, remember, is why there's an I here. So let's just, to check, we can plug this back in. Take two derivatives, you get minus k prime squared, right, times c. The c is going to cancel always, but two derivatives of that, and should I write? Yeah, I'll write it out. It's the same answer. I'm just going to write it out because, so this is the test solution. We know that it's because second derivative of something is minus the same thing, so there has to be an I here so that we get, when we take two derivatives, we get a minus sign. We plug in, we get c k prime squared, because two of those, minus because of the I squared, c e to the I k prime x, right? That's this side, equals minus 2m e minus v naught, okay, whatever, over h bar squared, times, and then psi again is c e to the I k prime x. That cancels with that. And now, and c cancels. And now we get, that cancels, and now we get k prime is the square root of 2m e minus v naught. Sorry, that's not a, shouldn't be a bar. E minus v naught over h bar squared. Okay, that's what I just wrote, but I just derived it by plugging this test solution in. So the only, when I keep, these are difficult looking equations, but you've seen that it seems that 99% of the differential equations you'll ever see, this is the answer. But you might have to find out what k is, like this case. K is a new thing, we don't care, but we want to put this. And the reason, again, the reason I called it k prime is because I know this is not the same as this k. So these are both k. This is, well, actually, oh, sorry, I'm sorry. There's plus a d e to the minus I k prime x. Because there's the other one. Now, of course, it's the same. Everything's going to be the same. Okay, so now the solution for the middle. So remember, this is all in region 2. So this is like region 1's here, region 3's here. This is all in region 2. You know it's in region 2 because there's a v naught. Now, here's where it's going to look a little different. We can't just write c e to the I k prime x up here. We could, but that would be incomplete. The reason is because remember what I said, e minus v naught is negative because e is less than v naught. This is the whole point of the tunneling. It's not tunneling if you just go over a tunnel. That's called, that doesn't even have it's not anything. Tunneling is when you go through something where you don't have enough energy. So this number, e minus v naught, is negative, but I don't like that everything in my square root is negative under my square root. That's weird. So I could change it to, I'm going to negate this. So it's minus 2m v naught minus e, right? Over h bar squared. And now I can take out the minus, the square root of a minus, and I can write this as I, right? So all I've done between here and here, this is still k prime, all I've done between here and here is just take out the I, and now everything in my square root is positive. So this is a real number now. I mean, sorry, it's I times a real number. So it's purely, k prime is purely imaginary. And now we have to plug k prime back in to here, and notice that we had an I already, and so the other I is going to make it a real exponential. So remember, e to the I things with x always give you oscillating things. That's like here, we had waves. That's why I drew it like this, and I'm going to draw it like that too. But when we have e to the real number, that's a decay or an exponential growth, right? And so if we plug that in, we get c e to the minus minus k, well, I'll just write the whole thing. Minus radical 2m e minus v naught over h bar squared x plus d, and there's, of course, remember the d is just the other one. It's everything follows, like you could just, the d is also comes along with it, because the only reason we got rid of it for these ones is because we only cared about it going to the right. So I guess that's true. You could forget about, I mean, you could also test it by saying that, like, the d is going to give you the same thing with a plus sign, and we know that makes exponential growth, and we know that we're not going to have exponential growth here. It's going to decay because it's going through a barrier. So this is the only one. The d is going to end up going away. I guess, yeah, okay. Let me. I guess you could think a better way to think it would be the simpler way of everything here is going to the right. So this is going to the right, therefore we only need the first term that goes to the right. We don't need to consider the second term. So now this is our three solutions. Now we're not actually done because we didn't apply any boundary conditions, and because we have three unknowns here, which is kind of weird. Now, it's actually going to be okay to have one unknown in this problem, the one unknown being the amplitude of the original wave function, because it would be impossible to know we just made it up, because we're just finding the, and if they ask us like the tunneling probability, we don't actually need it because we're going to divide by it at the end. It's basically we're finding like the percentage decrease or something like that. So now that we have these three, now we have to find, and remember, we found the three just by using this Schrodinger equation in the three situations, that's it. And they were actually almost identical. Despite how much is written on the board, we kind of did the same thing several times. And now we just apply the boundary conditions. And the boundary conditions are psi 1 at 0, if this is 0, must be equal to psi 2 at 0, and psi 2 at a must be equal to psi 3 at a. And obviously the reason we need to do this is because, of course, if we're describing a wave function, we can't just say it's like completely unrelated and different. It's not unrelated, it's a continuous wave function, so they need to be continuous everywhere. So we need to apply this. Now, of course, if we apply this, we plug in this, and we'll end up getting that if you plug in 0, you get just c for at, so the value of the wave function here is going to be c, and the value here is going to be a, and so a must equal c by this. And then here you'll get not c equals b. Well, this is now a. So you get this by boundary conditions. And then you get some relation here, as we showed last time. It's in the book, too. It's a much better explanation in the book. Well, it tells you all the math in the book. In the thing about tunneling. And it tells you that it's not going to be just the same, because these exponents are not equal. And, it's because if you plug in e to the I k a, this is the value, this is this side, and this side is going to be, you plug in A here, and as you can see, it's going to be some really annoying exponential, and they're not the same. Like this is K prime basically, and this is K, and so they're not going to cancel in a nice way. Anyway, so it's a little bit of a mess, but it's just algebra. You're just going to solve for B in terms of, right, and this is, I'll just write psi 2 at A. You can plug in x equals A for that. And of course, once you do that, everything everything here is going to be a number, not a variable. There's no x's anymore. Therefore, you can just solve for B just by dividing by this, and something cancels, I guess, and you get the thing that you get the tunneling probability it says in the book. And if you plot that function, it looks like this. It looks like a wave here. We know it's a wave because it's this kind. It's really implying the real part, so, but whatever. And then it gives you a negative exponential here because we have this negative, again, this is just a real number, so it's an e to the minus real number. So it's a negative, it's a decay like this. And then here we get another wave, but of course, the amplitude is going to be lower. It's not going to be the same. It's going to be lower because it has to match here and here. So once we apply the boundary conditions, then we plot it, we'll never have to pick up if we draw it, we'll never pick up the pen or whatever because it's continuous. That's the whole point. He mentioned, as he did in the other PowerPoint, he mentioned how the derivatives have to be continuous. Do not listen to that. Because none of the that's true except in some cases, and those are all of the cases we're doing in this class. So, which is when there's vertical bars for a potential. Whenever there's a square part of a potential, it does not apply. Which is all of the examples here, apparently. Okay, does that make sense? I meant to do this as an overview, but I kind of did the whole thing again. But hopefully that's good to see. And then the other thing I was going to do too, so hopefully I'll do it hopefully quickly so that we can get to whatever you want to talk about. The finite well, which is another bound state, but it is not going to be the same as this infinite square well. So the infinite square well, we solved the Schrodinger equation, and then we just applied the boundary conditions, and the boundary conditions were psi at 0 was 0, and psi at A was 0. And we know that because we know the wave function outside is 0 all the way up to the edges, and then we know that, on both sides it's like that. The reason we know it's 0 is because the potential is infinite, so no matter how much energy it has, it's sort of can't make any progress, can't push into it at all. It's like an infinitely tall wall, right? The taller the wall is, you can see here that the higher V naught is, the higher V naught is, sorry, this is backwards. It should be V naught over V naught minus E. Remember I flipped it here to give us the I that canceled, that did the other eyes. Yeah, sorry. So we can see here that the higher that V naught is, the more exponentially, the bigger the real number is here. So if we do e to the minus 2x, this is just a math detour. E to the minus 2x looks, I don't want to draw this, looks like that. And e to the minus 100x looks like, okay, I'm not doing this very well. The point is that e to the minus, if there's a really big number, it plummets to 0 very quickly, right? You get things here, let me try to draw it differently. That's a really fast plummeting to 0, and this is a very gentle one, right? E to the minus 100x has a much bigger plummeting to 0. It's very close to 0. And so if you make V naught higher and higher, you get e to the minus bigger number. Therefore, you get that if this was really tall, you would get that it has a very low probability of tunneling because it has to, in other words, you can think of it as the barrier, if it's really tall, it takes a lot of energy to overcome, to tunnel through the barrier, and therefore it'll sort of decrease very sharply. If it's infinitely tall, it will go to 0 infinitely fast. So that's sort of an intuition of why this is actually kind of a limit of this. Not quite. I mean, sorry. It's sort of the opposite. I mean, if you took this to infinity, it would be like an infinite barrier, which is not a problem we would do because it's boring. Because because nothing happens. Okay, so I'm going to erase all this, and then I'll do a finite well, which is another bound state that is more interesting, and I believe is on the next homework.
It's on the next one.
It is?
Well, I don't know.
Okay.
I totally guessed, but it's not on this one, is it?
Okay,
What
I
was
believe
trying
it's.
to
I
subtly
believe I
say.
saw it on the, not on the next homework. I saw it in the next chapter of the book.
He
I
hasn't
believe.
posted the next homework yet.
Okay,
Just
I wouldn't know
still-
because I don't
Never
use Blackboard,
mind.
but
I'm really behind.
It
If we
looks-
take anything
it
away from
looks-
this, I am not on top of
It
my
looks phenomenal. I'll tell you that much.
oh, okay. I just remembered one thing. I need to do 3D version. Okay, sorry. 3D infinite square well, and then I'll do finite barrier, or sorry, finite well. So I'll just really quick talk about the 3D one. The 3D one is identical, so the Schrodinger equation looks the same, except we have this, and this is just d squared dx squared plus d squared dy squared plus d squared dz squared, right, of psi. That's just that nabla.
Right.
And so then we have, and let's say you had a cube. So think of this as identical to this thing we just did with the infinite things, but now it's just, there's only a cube of free space and everything around it is infinitely, like it's just like you put a sealed box and you put a particle in the box. Well now, now you can imagine that in each dimension you actually get, it's its own one-dimensional, so in the x dimension, this is x, and this is 0 to a, and this is so this is the thing we just did, but you also get one in the y dimension, y, from 0 to a, and you also get one in the z dimension, and you actually can solve this is separable, you can actually solve the Schrodinger equation in three separate dimensions, and your wave functions are just going to be like, it's going to be like, so remember how for this, the ground state was this, right? It was like half of a sine function. So this is x, this is y. The ground state looks like this. So the ground state in here is going to be like, it's like this in all dimensions. It's like well, I can't even draw it because I need to draw it in a fourth dimension for the height. But anyway, because there's nowhere to put the energy in there. No direction to put the energy in. Anyway, but for the first excited state, remember the first excited state was like this, right? But now I have three choices of where to put my excited state. I could put it in the x direction, y direction, or the z direction, right? Like, meaning I could make the wave function in the x direction look like this, or the y or the z. So if I plot my energy levels, right, I have the ground state, which is n equals 1 for x, y, z. So this is n equals 1, but this is, I'll actually call this nx equals 1. This is ny equals 1, and there's I'm just not going to draw a z, but there's a z, right? So the ground state is when nx equals ny equals nz equals 1, right? But then when I take my first excited state, instead of just saying, oh, it's just the one where you change the wave function to be like that, and the energy now is like, it's like n squared, pi squared, a squared, so you just change n from 1 to 2. Well, now you change nx from 1 to 2, but ny and nz are the same. And so now, this state, this first excited state, actually has 3 copies of it. There's 3 states that can be here. There's 3 possible sort of versions of this state. There's nx equals 2, ny equals 1, and z equals 1, or nx equals 1 and y equals 2, right? You see what I'm saying, right? It's not just like the single one-dimensional version. where you just get a single number that tells you which energy level you're at. This one you get it's that same thing, but you get 3 dimensions of them. So the wave function can be excited in the x direction or the y direction or the z direction or 2 of them. What if 2 of them were excited? Well, then you actually be in another state, which would be like a second excited state. Or what if one x was 3 and the other ones were 1? That's actually now a very complicated problem because how do you know which one's higher? And you could actually solve this and get a thing that's like E, and I think it's going to be like nx squared plus. It's going to look like this: pi squared h bar squared, or 2ma squared. This is the answer. Now I'm not going to solve it, but it looks like this. The reason it looks like this is because it's separable. So you actually get just each one added together because the total energy is just the sum of the energies in all the directions, right? So you get, if you just crossed out ny and nz, it would look exactly like a one-dimensional version. So anyway, this is the answer, but now there's 3, it's called 3 quantum numbers because there's 3 integers that you have to specify to tell you what state you're in. And therefore you could write psi. Now psi of nx, ny, nz would just be, it would be like sine n pi x over whatever times sine of n pi y over a times sine of n pi z over a. Anyway, I'm not going to write the whole thing because we're not going to do it, but it's literally just, I think the point that he was trying to make is that he drew it like this. There's 3 states here. Like you draw the 3 lines. It doesn't mean anything that they're over here. It's just to show that there's 3 distinct, not the same states that have the same energy. Because of course, if you plug in 2 for this one and 1 for the others, or 2 for this one, 1 for these, it's obviously the same energy. This is called like a degenerate state because there's more than one way you could configure that. So that's the 3D version. So as you can see, it's actually not, it's not that much hard, like there's nothing new in terms of like, it's not like you have to solve a different equation. It's just that when you plug this in, you actually can separate it into just 3 separate equations. Of course, the total wave function is going to be just the product of those 3. So it's just going to be sine. I feel like there was some thing where we did this with waves. I don't remember. But anyway, there's something where we did this with waves where we had to consider 2 dimensions and it ended up being like sine of nx times sine of ny. Like it's just the product of the 2 solutions. Anyway, the whole point of this is that we've seen that there's like energy levels you can occupy, but because there's multiple dimensions, there are multiple energy levels multiple states at the same energy level now. Usually you can't. Usually that doesn't happen. There's only 1 at each, but now there's multiple. And if, of course, if you're dealing with things like electrons where you can have 2, they come sort of in pairs, then maybe you have 2 here and 6 here and whatever, you know. So that's all just other details that I have to tell you though. Okay, does that make sense? How does everyone feel? Okay.
Makes sense.
Some mixed reactions. Hopefully this is. Oh my God, these
Didn't get you new markers.
last like. Of course not. They last like 90 seconds. All right. I'll just use this one. Okay, now I'm gonna do an actual new problem. You won't be surprised that it's gonna be basically the same thing, but it's gonna be a finite well. Because, and the reason I want to do it is because it's different than the other one, so I won't be saying the same words again. But we still are going to solve the Schrodinger equation in 3 regions. So the finite well, let's say we have, let's just call this energy 0 up here and call this energy minus V naught. Is that okay with everyone? I know it's a little weird because we're saying that something has a negative energy, but again, as usual, with height, with potential gravitational potential, we can always just call the height whatever, so it's the same thing. And we'll call this x equals 0, and then we'll call this x equals a, as you usually do. So this is not the same as the infinite well, because in the infinite well, we knew automatically that outside the potential was so high that we couldn't have any wave function out there. It would be 0 outside. So we could have written 1, 2, and 3 in that case. But in 1 and 3, it would be equal to 0, so it would be sort of stupid. Now, it's not that. That's not true. No matter how much energy we have, let's say we have energy E, which is, we're going to say that E is less than 0. E is less than 0. And E is greater, absolute value of E is greater than absolute value of E naught. I want to be very, I'm gonna get confused with the negative sign. So, but all we're saying is that E is above this and below this. That's what I want to say. If E was up here, it would like be a free particle and then a freer particle and then a less, it wouldn't be interesting. In this case, it's a free particle inside. So let's do, I'm gonna write the same thing I've been writing for.
You said you wouldn't get tired of it.
I'm a little tired of it, to be honest. E minus V naught. So I sort of keep rearranging where I put the V of X. Keep rearranging where I put the V. Obviously, it should be all the same. Function of X. Again, this is we're back to one dimension. Thank God. Because I just put an X everywhere. I didn't put Y and Z. And now let's do, so we have psi 1, psi 2, and psi 3. Oh, dear Lord, this is getting worse and worse. All right, let's just try this. I know where they keep the markers, so maybe I can know in a second. So let's do psi 2 first because we kind of already know how to do this. It's just going to be, I'll say A again, because why not? E to the I k x, right? Actually, let's do plus e to the minus I k x. Actually, sorry. So we can say this. I actually want to use the sine and cosine version. It's, of course, as we know, it's identical. It's not identical, but it still solves the equation. But I want to use the sine and cosine because we know it's a wave and it's not like, I don't know, why not? We might as well. Just because it's different than the last one. The last one we did it with the I. Now we could plug it back in here to find what k is. Remember, again, I made up k. We can find what k is. We're actually, no surprise, we're going to find that k is radical 2m E minus V naught. It's this V naught now. Actually, sorry, it's going to be E plus V naught because it's minus negative V naught, right? Over H bar. I'll unsquare it, take it out now. So we obtain K by plugging back in this. Now, of course, if you just remember that K is always like, if you rearrange this, that's fine too, but whatever. So don't worry too much about this plus sign. The only reason it's different, it's not actually different. The only reason it's different is because I called this negative. If I changed up things, it would be different. So, okay, now we don't actually have any boundary conditions yet because we don't actually know we don't know what's going to happen at the end. Of course, we need to set psi 2 equal to psi 1 at 0 and equal to psi 3 at A, but we don't know those yet. So let's do psi 1 and psi 3. Well, this is going to be, it's going to be like that. But now E, remember E is negative, right? Yeah. So remember E is negative. It's less than 0. And so we're actually, it's going to be like, prime, K prime. So that's just the solution to this with no V, right? So this is the free particle solution. It looks like the free particle solution. It's actually not going to be. And the reason is because of the same thing as last time where we ended up getting that K prime had a negative number in it, or K prime had an I in it. And so if we do that again, we get K prime is radical 2m. It's just E now because the V is 0 in region 1 over H bar. That's it. But remember, E is a negative number. So we probably shouldn't have that here. So we can write this also as I radical 2m, and then I'll write the absolute value of E. So we can write in, this is going to be in terms of the absolute value of E. In general, you shouldn't leave things in exponentials that aren't clear whether they're real or not. You should always have just real. You should have i's and then real things. Does this make sense? Why I did this? I did this because e is negative, and if I just leave it as e, it's very sort of. It's almost like I'm tricking someone. I don't want to fool anyone into thinking this. If this is negative, that means that this is actually an imaginary number. But I don't want to just make it mysterious. I want to actually explicitly write that it's imaginary. Now, this absolute value of v is a positive number. This is positive, therefore this whole thing is real times an I. Now, if I plug k back into here, k prime, I should say, I get a. Oh, sorry, I shouldn't use a and b because I used a and b here. C and d. Sorry. So now I get c e to the. Now it's going to be I k prime x, but k prime has an I here, so it's going to be e to the minus radical 2 m e absolute value v over h bar x. I'm realizing now, I'm not going to change conventions now, but I'm realizing now I probably should have called this minus e. It would just make everything easier. But whatever, we'll just use absolute value v for this. Plus d e to the, and now the I is going to also do this, but of course minus I times I is plus 1. So I'm going to get e to the plus 2me over h bar x. Okay? Okay, and now let's just do region 3 real quick. What's going on in region 3? As with the other, whatever the problem we just did, the barrier, right? With the tunneling problem. Just like with the tunneling problem, region 3 is identical to region 1. Everything's exactly the same. The energy, the particle still has energy E, and everything's exactly the same. So the solution is going to be the same. Of course, it's not going to have the same coefficients because those are arbitrary. Any value of these solves this because they cancel. So we're going to, of course, have to use E and F. I don't want to use E because E is energy, so I'll say F e to the minus radical 2m e over h bar plus g e to the 2m. Okay? Does that make sense? So hopefully it makes sense why I changed the coefficients here, but I cannot change this. This is going to be the same. I mean, I could put another k and just plug it in, and I would get the same thing, of course. Okay, so does that so now we have 6 unknowns.
So no x in 3.
Sorry. Yes, there is an x. Yes, okay. Now we have to apply our boundary conditions, obviously. We know we have a boundary condition here and here, but we have 6 unknowns. That doesn't seem like, too many, right? Too many unknowns. But let's just see what happens. So let's apply the boundary condition x equals 0. So we know that psi, so I always write what the boundary condition is first. Don't try to do it all at once. Psi 1 at 0 equals psi 2 at 0. What do we get now? We'll plug in 0 and we get c plus d, right? That's psi 1 at 0. And plug in psi 2 at 0 and we get at 0 we get b, right? Okay. And then we plug in, and then psi 2 at, the other boundary condition, psi 2 at A is equal to psi 3 at A. And this means that that we have A, okay, this is going to be annoying, A sine Ka plus B cosine Ka. Is going to be f e to the minus radical 2m e over h bar plus g e to the 2m. This is the point where I point out that, oh sorry, A, that these are all numbers here. There's no more x's here. So if I want to solve for, let's say, so here I get something. Actually, yeah, okay. Now, okay, so there's all numbers here. You could plug these in and simplify it a little bit. There's something else, though. This is the main reason I talked about this problem, is that there's another thing that I actually should have done before this step, but whatever. Other boundary conditions that we need to apply. And they're not boundary conditions here. Now, we knew that the psi had to, so we know a few things about psi. The psi has to be continuous. But we also know that psi has to be normalizable. So remember I talked about this last time. Normalizable means that if you square it and then integrate it over all of the x dimension, this has to be 1, or has to be basically a finite number, because of course you could just scale it you could just multiply it by any number. But if it's infinity, that's a problem because you can't get rid of that. That's non-normalizable. So this is a new fact. This fact doesn't come from the Schrodinger equation. There are things that solve the Schrodinger equation that are not true for here. But this is actually a fact about wave functions. This is like a new quantum mechanical postulate, as he says. So it has to be normalizable. Now, if you look back at these functions here, we just wrote them down because that's what we get, and that's fine. But they don't actually all satisfy this property, right? So now I'm going to do something exciting. What do you think we should conclude from this? You three. They don't know who you are on camera, so that's... So what do you think of all these? So we have 3 solutions, right? What do you think we could say about any of these solutions based on the fact that psi has to be normalizable? Meaning if we integrate it over, now remember this means that. Okay, it's a tough one. Okay. So excited. So what it means is that, remember this, so this function, let's look at psi 1. This function is some number times e to the, this is a real number, x, plus this, sorry, minus this, and then this is a plus. So this e to the x looks like this, right? And e to the minus x looks like that, right? That's just how those functions work. So if we look back at this function over here in this region, our c valued, if let's say d equals 0, let's just say we found d equals 0, what will this function look like? We get c e to the minus a real number x. That means it's actually going to look like that, right? That's what this part looks like. And actually, we don't even need to say if d equals 0. For any number, eventually as we get more and more negative x's, right, if x is negative 1 million, which is way out here, x being negative 1 million, well, that cancels this as 1 million times whatever, e to the million is a huge number. And then this will be very small because minus 1 million will make this very small. So what that means is that, oh, thank you.
You can never say I don't love you guys.
As we go to very big negative numbers, this will actually blow up to infinity, right? No matter what we choose for C and D, right? Does everyone see how that makes sense? I know it's a little distracting.
Honestly, no, I was focused on the pizza. What did you just say?
Let me just finish this point. That because this function, no matter what we pick for C and D, no matter what we pick for C and D, for any numbers, as we get to x goes to negative infinity, this will blow up. This will go to infinity because of this term. So this means that to make it, and that will be non-normalizable, because then if this blows up to infinity, well, now we can never take the integral and have it be 1. It's going to be infinity. So actually, there's a boundary condition. Where do I want to write this? There's a boundary condition at x equals minus infinity. Right? So this is more important than black. This is a red level importance. X goes to infinity means psi has to go to 0. Imagine if, it's plus or minus infinity. Because imagine if x goes to infinity and psi went to any other number, then when you take the integral over all of space, you'll get infinity, right? If psi went to 1, right, the integral of 1 over from negative infinity to infinity is infinity. So the only thing you could possibly get such that the integral over all of space is a finite number, is less than infinity, all right, for finite, this has to be true on both sides. So in other words, what that means is that if you look at the wave function, it has to go like this at the ends. If it goes like this at the ends, it's going to, the integral, the area under the curve is going to be infinite. So those boundary conditions say that this is 0, and it also says the same thing over here. We can't have it blow up to the right, like positively to the right. So this one has to be 0. Right? It's the opposite. The negative one is okay because the negative one is like this, and the positive one on this side is like that. That's it. So now C is 0, so we get that, and G is 0, so this goes away. And of course, it's still a little complicated. This particular here is numerically complicated, just like the tunneling problem. But these are all numbers, so you could find everything. You would still have a few unknowns because of life that happens. But anyway, okay. So does this fact make sense? This is a new fact, which is you have a new boundary condition. Psi has to be continuous, but psi also, this is like 1 and 2.
It's like a middle school sleep.
Yes. Mom brought us
Diet Coke
pizza and Diet Coke. Yeah. Okay. That's all I wanted to say. Does everyone understand? So in other words, continuous gives us boundary conditions, but this also gives us another boundary condition at infinity, which is this. We can take a break.
All I can smell is
I'm good. This is literally all I wanted to do for today. So we'll spend the rest of the time doing whatever you want.
Thank you.
Love.
It's a great idea. It's gonna be like homework questions.
Yeah, so the homework.
Yeah. Say, just so we're clear.
For next week.
Fair enough.
No, but that one was ruthless. Sorry, people on camera. Yeah, I just looked at it.
Yeah, it says compare the difference in the first two energy levels in these two cases for number 5. How are these
Sounds like a
two cases?
poor way to say it.
Yeah, I was like, what's that asking? And what's that all about?
So
Did you guys try to figure
That's about when we gave up.
It stopped at 5.
Yeah.
I think it's
So I'm right on target.
Solid.
so we found the formula for. I'm gonna erase this.
Sweet.
It's okay.
You got it.
Yeah, I got Sorry.
No,
No, you're good. You're good. I'm talking to Joe. Sorry.
So we found the formula, and it looked like. I know people on the camera don't like red sometimes, but Hopefully they'll be okay.
That sucks.
Should be here. What?
So this is the energy for the nth level of an infinite square well. Now, if you double the width, A is the width, right?
Right.
Yeah, that I
And
get.
N is the level.
It's good to know.
And so, I think what they mean is that do one thing with A. For width A, what's E of N? Was it N plus 2? For a difference in the first two energy levels. So I think that what they want you to do is find E2 and E1. Those are the first two energy levels for width A, and then find for width 2A, E2 and E1. Oh wait, sorry. Let me look at it again. Compare the difference in the first two energy levels. So maybe they mean the actual like the difference, like minus difference. Whatever, it doesn't matter. As long as you write some of these things, it's fine. But I guess what they mean is put 2A here. I mean, it's kind of, okay, it's going to be over 4. That's not a big surprise. That's the big thing. They're all going to be reduced by a factor of 4. Which is kind of interesting. That if you double the width of your well, all the energies drop significantly. That's sort of not obvious. You might think, make the well bigger, you have bigger energies in there. I don't know, but I guess not. I guess, well, whatever. I don't care. I'm just realizing there's no like good intuition explanation. I think for this, so it's not going to be satisfying.
Alright. I'll take it. Okay.
Oh no, there is an explanation. So I'm sorry. Let me give you an explanation. If you have a narrow well versus a very wide well, the wave function, well, you can definitely fit more energy levels in here. Okay, never mind. That's all I have to say.
Okay.
And therefore, the wave functions will be sort of more like this, whereas here they'll be like that or whatever. If that reduces the glare.
I would.
Oh.
So the top half is like totally gone now.
Where's my
Oh, yeah, you're right. It's actually I do need to transfer that.
It's hidden right now.
stomach was starting to.
Yeah, that's still a little. Yeah, it's
Do you
fine.
eat?
Yes, I did a lot today.
We call it a tree.
Everyone good with this
Yeah.
problem?
Wait, 6 is like kind of the same thing. Yeah.
Oh.
Yeah.
I set that up. Oh, you did.
Oh yeah. Yep. So 6 is the same thing. You just but you don't plug in. Like when they say first two energy levels, the first one is 1, the second one is 2. When they say the nth energy level, well, it's just this.
Okay.
So the n plus 2 is you just plug in n as n plus 2. I wrote that out yesterday on or Monday.
Yeah, I'm just copying it down.
It's sort of like a really annoying algebra thing. Like it doesn't come out with anything nice for some reason.
That's 7. Oh,
That's nothing.
yeah.
6, 7.
Compare and discuss your results? No.
Ow.
I'm not doing that. No.
Ew.
Like middle school, I'm not doing that.
7.
Yeah, look at C. Compare and discuss.
But you have to discuss.
I'm here.
Yeah, whatever. Okay, so there's just whatever. A lot of plugging into this formula. know.
Is it that same one right there?
If it says infinite quantum well, then yes.
Okay.
This is the energies of an infinite. I'll even write it. Energies of an infinite quantum well.
And you don't have to.
Put it in quotes because that's what they call it in the book. But I would call it a square well. Because all quantum wells are infinite, I suppose.
Okay. And then you just put in like N1, N2, and
Yeah, sure. And then M would be the mass of the particle. A would be the length. And they put L, I probably, whatever.
They did. It's
H bar, you'd have to make sure you put, because if you want the output in, this is the only thing with energy in it. So if you want the output in joules, you have to use the joule version, which is like 10 to the negative 34, whatever. If you want the answer in electron volts, you have to put or in electron volts, which is some other number, I don't know. But pi is pi.
Oh wow.
Make sure A is in meters, I guess.
First three.
Okay. Once I tell you to put something in meters, it's like I've lost all interest in it. It's not physics anymore. This is like checking things.
Mhm.
Or joules, who cares? What's a joule?
You see, we do.
That's
Okay,
what
good
we're
luck.
on.
Yeah, you're
Okay.
you're different.
Okay. 8.
First three energy levels.
So 8, you're just solving for A.
N is 1, N is 2.
8, you're solving. Let me.
Trying to
Yeah,
find
they're
the
gonna be the
width
same.
of the well.
Oh wait, well, he's gonna change.
Like, what do you
A's
have to
gonna
make those
Oh.
conditions in order? Just find the.
Oh,
Yeah,
yes.
areas
Okay.
It's the same
associated with
width.
it.
Yeah, so that would be. That's actually okay. That's a good question. We want.
What was the question?
That's a good question. The question was about. I forgot what 8.
8.
We want a photon, so we want photon in visible range. Now, how do you know what that means? You Google it.
I was gonna
And
say-
then you find either a frequency, nu, or F, I think they used, right? I'll use F, I think, because they used F. Frequency or a wavelength. Then, from this, remember we had this, HF, for a photon,
Mhm.
or also, what was it, HC over lambda? So then we can find the energies. Remember, a photon is only defined by one number. It doesn't have a mass. It doesn't have any of. It's just like an electron has a mass, an electric charge, a velocity, a momentum, right? A photon has exactly one thing about it, and it's could be written as the energy or the frequency or the wavelength. Those are all you could just convert between them because all the other numbers in here, H and C, are constants. So anyway, look up photon in the visible range. Look up any of these things. Find the energy. And if we want a transition, so remember, these are the allowed energies. So if we have a photon in one of those states, sorry, not a photon, if we have a particle in one of those states, and we want it to emit a photon with a certain energy, that means that the difference in energy between those levels has to be that much, right? Energy is still conserved here. Someone asked that in class yesterday. Someone asked, how is energy still conserved, I mean, and there was an answer that I didn't think quite was a good answer, but it was answered, and I was about to stand up and answer myself. Anyway, the point is that it is always conserved, meaning if here's the allowed energies, if here's the square well, here's the allowed energies.
Mhm.
If we want a particle going from here to emit a photon, or a photon of a certain energy going from here, like if we want it to absorb and go to the next level, that means that this energy difference between these two must be equal to the energy of the photon.
Okay.
Now, of course, that doesn't mean that E1 has to be that energy. That's impossible. That's not true. So you don't just set this equal to the energy of the photon, because that would tell you if you had zero energy, then how do you go up to the first energy level, which is impossible because you can't have zero energy in this quantum well, as we showed. The lowest zero, remember, is actually, that's a good, let me just call back to the thing, we know we can't have zero energy because zero energy is associated with the wave function that's flat, right? And that solves the Schrodinger equation, but it doesn't work because. You remember why it doesn't work? It's not normalized. Exactly. It's, the reason we can't have psi of n where n equals 0 and therefore e of 0.
Wow.
The reason we can't have these, even though they solve the Schrodinger equation, for a string we could. It's fine. It just doesn't make a sound, but whatever. We can't have this because it's not normalizable. Because the integral over all of space is 0. There's no thing we can multiply to make it 1, so it cannot be normalized.
I want my degree now.
That's excellent. Extra points,
Holy shit.
even though I have no.
And the homework.
Ability to
and
do
I
that,
get
but-
all of this wrong. You're just be
Yeah.
like, she said normalizable.
That was
in
good.
office
Yeah, yeah, yeah.
hours."
So normalizability came up several times because it's a new. That is a new thing. It is a string, a guitar string does not need to be normalizable. No one cares. It just solves a differential equation. This is a new thing. It solves a differential equation, but we also care that it has these other properties because it's a new sort of field. That's why it's quantum mechanics and not just like small waves or something. They would just call it like particle small waves if it was normal. But there's these new properties and then anyway, whatever. So anyway, so that's why the lowest energy. Well, I don't even know what I was talking about. We know that that you can't have zero energy in this world. The lowest energy you can have is E1. So if we want a particle to emit a visible photon, that if we want something to happen in infinite square well, such that a visible photon comes out, we would need that. Let's just pick two levels. We don't. You could pick any two levels. We could pick 5 and 6, or 5 and 2. But they don't have to be next to each other, right? All we need is that the difference between them. I'll pick 1 and 2 for just make it easy. E2 minus E1. This is if a particle goes from E2 to E1, it will emit an energy equal to this. Therefore, we want this to be visible. And of course, E2 and E1 we know from this. And therefore, when we do a bunch of simplification and we have a number here, we could solve for these are constants. N is going to be 2 here, and N is going to be 1 here. M is going to be given because of whatever the particle we have is, or we could find it, I guess. And A is going to be, I think A is what they want you to solve for.
Mm-hmm. Like
So-
how wide it is in order to get.
Yes, and it says an electron, I think, right?
Yeah.
Yeah, so of course, therefore we need the mass of the electron.
Oh no. Yeah.
Okay, good, yeah.
Just gonna keep saying.
So does that make sense? This is literally, so you probably, it depends, I don't know what they teach in chemistry, but in chemistry, they teach extremely similar things to this, but they don't teach it in a quantum mechanics sense
No, they do not.
because they just tell you that there's energy levels of atoms, and you just think that's a thing about atoms. It's not a thing about atoms, it's a thing about quantum mechanics, about electrons and how they work. It's just that this is actually the simplest example, and atoms actually really complex, so they just tell you all the answers. But this one we can actually, because we know the formula for it, actually in an atom it's not that much more complicated. I think it's like 1 over n squared. You did chemistry, right?
Biology, but yes.
Okay.
It's been a minute.
Someone did, yeah. It's something with like 1 over n squared, right?
What are you referring to?
Sorry, the energy levels of the electrons in the different shells.
That sounds right. Yeah.
There's something with it, and you have to do. I just remember doing problems like I and F,
That was way more into organic, so you're getting
R,
into
something.
inorganic.
Anyway,
Does
yeah,
that sound fun?
okay, something like this. Forget about this. The point is that this is the formula for the square well. This is the formula for a Coulomb potential in 3D that we're not going to do yet. But I could talk about that in a second because it is in the next chapter. But let's get back to that. This is the formula which we found explicitly. It was relatively easy to find because we just had to do the boundary conditions and all that stuff and then plug in, find E. And we get this formula, and now we have it, and so therefore we can compute any emissions that come from this or absorptions have to be because of differences between two energy levels are equal to that is the energy emitted and absorbed. And it's always absorbed and emitted in the form of a photon, pretty much. So if they ask you, how do you get a photon out of this like what do you have to do to, or if you emit this level of photon, what will happen? Let's say they said this is an example problem. Let's say they said you have an electron in the second energy level of a square well with blah blah blah, and you send this wavelength photon in it. Will it be absorbed, and what will happen? You could just say, well, I'll take the energy 2 that the electron has already, and add to it the energy of the photon that you're absorbing, and you get a new energy, E prime, and then we just have to E prime equals this and just like solve for n. And if n comes out to be 5, then therefore we know that that could happen and it would go from E2 to E5, right? If we get n equals 1.6, then it would be impossible because they're integers, right? So if we get 1.6, we would say nothing happens. It cannot absorb, and it will not change energy levels. So that would be good if I was making like a quiz, which I'm not. I'm not trying to like subtly imply. I really am not making the quiz. But if I was, that would be a good question because it's just taking this formula that you know, and hopefully can derive given a little bit of time. I didn't want your faces changed slightly, but hopefully can derive given a little, just and maybe some like guiding hints, like just obviously given the Schrodinger equation, given boundary condition. Anyway, eventually you could get this, I think, right? From that, you know all the properties of energies in here, and given new energies, you know the principle. The principle that you have to know that they won't tell you, that you have to know that's new here, is that you can only be in these energies. So therefore, emission or absorption of energies that are not differences between two things here will just not be affected by this. That's the quantum mechanics thing. Well, what was I going to say? Oh, okay. Is that good for everyone? I was going to mention one thing about, because it isn't specifically in the book, the hydrogen atom in 3 dimensions. I will just mention what it looks like, what the Schrodinger equation looks like for that. I will not solve it because I don't know how to solve it. It's really hard. But remember how, okay. Good? Okay. Remember how the Schrodinger equation, when we did it, we just did it in 3 dimensions, and we got that there were degenerate energy levels. There were multiple quantum numbers. And to get an energy of a state, or not even to get the energy of a state, but also to get the wave function of a state, you have to tell me all 3 of those quantum numbers. For the single dimension, you only have to tell me one number that tells you everything you need to know about. It tells you the wave function, it tells you the energy, and you can solve for everything from that. For the 3D version, it's just this in 3 dimensions, so you have to tell me the number in each dimension in x, y, and z. For a hydrogen atom, what we have is that, you could write it very simply as V is 1 over R, but if this is in 3 dimensions, R is not just, it's not just like I wrote 1 over X and then we could do some clever math and I have a special solution. It's actually really, really hard because R is in polar coordinates, in spherical coordinates. So of course we could also write it as that. Now, if you plug this in here, or in here, it's impossible. No one has ever done that. It's impossible. However, you could do this whole thing. This is in, I should say, remember when we did this? I'm sorry, I'm not organizing this very well. Z squared. When I said we use this as the derivative here for the 3-dimensional one, and I said, oh, look, it's easy because it just separates. It looks like just 3 equations added together, and it is. And that's how we did it, and that's how we got 3 copies of this, basically, with X, Y, and Z. So that's how we do it. Now, to do a hydrogen atom where we have 1 over R, where R is the distance from the origin in 3 dimensions, we actually have to go from X, Y, Z to a different coordinate system, R, theta, phi. This is spherical coordinate. Have you used this before? Did I talk about this in the math? I don't think I did talk about this in the math review.
That's way back.
Yeah, that was a while ago.
You're bringing
you got the quantum in the review, I would have walked out.
No. This is just this could be used for any classical like.
All right. Well, yes,
So-
probably.
So
I've
this
seen a
is
meme about this, but I don't know if I actually.
the one with the woman with the cone equations around her. do you know
Oh
that?
no, well, that's not what I was referring
Oh,
to, but
okay.
it's probably in there too.
That's one of my favorites. So this is XYZ, R theta, and I'll just say real quick, R theta phi, because I'm sure he's going to explain this in class at some point. R is the distance from an origin point, just like you have to have an origin here. R is distance here. Theta is the latitude, right? So on a globe, globes use these coordinates. You don't usually say R because you're probably on the surface of the Earth. But this angle here is theta, so that's your latitude. Of course, on the real Earth, we call this 0, but usually with this, we call this 0 and then this 90, or 180, sorry. So literally it's your latitude, so the equator would be at theta equals 90 degrees, or pi over 2. So that would be this, and phi goes around the circle, so that would be like the time zone. So on an Earth, we use just these two because the radius is just constant. So this is like latitude and longitude. Latitude and longitude. That's literally what it is. So the point is that you could describe things with x, y, and z just fine, but some things like gravity works like 1 over r. If you tried to write it with x, y, z, it would be that square root thing. That's a nightmare. So you'd always do things with r, theta, and phi, because many electric fields work like that, 1 over r type stuff, and so things tend to work better this is spherical coordinates. And this is called Cartesian, right? Cartesian, like Descartes. Named after Descartes, so you know. The philosopher. Anyway. So these are spherical coordinates. You could have there's other coordinates like cylindrical, where you have like r, theta, and like z instead. It's kind of a weird one. Anyway, whatever. Some problems make it easier. The point is that the reason I am introducing spherical coordinates is because now that we have hydrogen in 3 dimensions, we actually do need to use this because now our potential just looks like 1 over r. It's actually going to be easier. But now instead of the Laplacian looking like this I have to convert to spherical, right? And you might think, oh, it's probably going to be d squared over dr squared and then over d theta squared. That's probably right. Like that looks like what it's going to be. Not even close. Not even a little. It's awful. It is. If you look up, so you could look at some Wikipedia, but it's just a nightmare. It's a horrible mess. I literally can't even write it. I don't even. Actually, I'll try to write it. It's like this is the first one, and then it's like r squared sine theta d theta. I'm sure I'm getting some of this wrong. I think it's this plus. R squared cosine theta sine phi d phi maybe. I don't know. There's no way this is right. I'm not even going to write it. But anyway, it looks kind of like that, but it's horrible. Literally, if you Google Laplacian, which is what this is called, Laplacian in 1 dimensions is this. So you might don't get scared with the word Laplacian. Laplacian is literally just second derivative, but it means you could have sometimes more than 1 dimension. So we've been doing things with Laplacians forever, but Laplacian, if you Google or Wikipedia Laplacian spherical, you'll see the whole thing. It has these coordinates. It looks like a nightmare, and that's why it's so hard to solve. But you do get quantum numbers. So the solutions look like this. I can't even write them. They're just so annoying. There's I'm not just saying this to like show off. I literally think he will show you this in class. So don't get annoyed that I'm like writing all these. So it looks like this. It's separable, kind of, where you have a part that tells you about the radial direction and a part that tells you this is called a spherical harmonic. It doesn't matter. Spherical harmonics, it's called, and it's solutions to things on a sphere, essentially. So it's kind of like how we use the boundary conditions of square well had to be 0, and we got a guitar string. You should count how many times I say guitar string like in this month period. But anyway, when we find the solution on a Carr string, we say the boundary conditions are that they have to be 0 at the ends. On a sphere, the boundary conditions are that they have to go back to their starting point when you go around 2 pi, or, yeah, 2 pi, right? If you go around 2 pi on phi, you have to have the same value you started with, because that's what a circle is, right? That's what if you go around the equator, you better be back to the normal. So the boundary conditions are actually kind of more interesting here, because there is no boundary, it's actually a closed manifold. I'm getting too far into this, but you know what I mean. There's interesting boundary conditions that you get certain solutions called spherical harmonics. They're used for tons and tons and tons of stuff in engineering. Probably, maybe not ones you've used, but I don't know because I'm not an engineer, but I assume they've used in engineering because they're solutions to differential equations on spheres. They're actually solutions to like the guitar string problem, but on a sphere. They're called these spherical lines. But there's also a radial part. The whole point of this, the only thing I'm trying to say about this is that you have 3 quantum numbers. Again, quantum numbers means things that tell you what state you're in, things that describe the wave function, so psi. 3 quantum numbers, and remember as I said in the last thing, a quantum mechanics problem is one where you start with a potential V and you get psi and E. So again, that's all I'm trying to show you here, is that we get psi and V. We started with V as 1 over R, and we get psi depends on N, L, and M, okay? It looks like that. N is called the principal quantum number. So this is like this is like the first orbitals of a, not orbitals, is that what, yeah, that's what they're called. Like the N equals 1 of an atom and N equals 2.
The shells.
The shells, thank you very much, the shells. This is called the principal quantum number. This means quantum number. L and M have other names. This is called I don't remember. M is called the magnetic quantum number, and L is called the something, doesn't matter, whatever. It's called something. If you need to know it, he'll tell you in class, which I believe he will soon because it's in the book. The other cool thing is that E should depend on all 3 of these, but actually E only depends on N, sorry. That means that the shells in each of the shells of an atom, electron shells of an atom, of a hydrogen atom, the energy is the same in each shell. The N equals 1 shell has some energy. The N equals 2 shell has some energy, but there's actually a bunch, and they're all labeled by different other things. So remember, have you ever seen again, this is like a chemistry thing if you've seen it in your chemistry class, where they draw the orbitals and they draw like the sp. This L is like spdf. You've seen these? So this is L equals 0, this is L equals 1, this is L equals 2, this is L equals 3. So the spherical harmonics give you certain values up to n. Anyway, there's a whole other thing that relates them together. They're not independent. But when you have up to L equals 0 is called the s orbital or whatever. L equals 1 is called the p orbital, and then you have the 1. Yeah, you have the 1p and then 1s, 2s, 2p, 3s, this orbital diagrams. Yeah, that's this. The 1, this is n. L is the s. And then m is as the thing about electrons. It's the fact. So if you had things without electrons, it would just be these. But because we have electrons that can be spin up or spin down, they have an extra little thing. It doesn't really matter. Anyway, that's m. M usually you don't. I don't think you're right. Maybe you do. I don't even remember. Anyway, m is something else called the magnetic quantum number. But that's it. So this thing from chemistry of the names of the shells are literally solutions to the Schrodinger equation, just like this was a solution to the Schrodinger equation with different ends. Of course, because of some weird things, we get 3 quantum numbers. There's no real, I don't know of a good explanation of why there's 3. There could have been 2. There could have been 7. Somehow there's 3 quantum numbers. And for miraculous reasons, the energy only depends on the principal quantum number. So in other words, 2s and 2p orbitals have a bunch of electrons, but they all have the same energy. So if you plotted the energies, it would be 1s, and then all the 2s, so it'd be like 1s, 2s, 2p, and you have 3s, 3p, 3d, or whatever. I don't remember how it works. But anyway, actually, well, whatever. I'm not going to get
They're
into
like
it.
mixed up somehow.
They're somehow mixed up. What
Yeah.
the point is
It's
that the number is the n, and that's the energy one here. Of course, in the this one, there was only one quantum number that is in both things. I should just write the wave function. And actually, we should normalize this. Oh, we did normalize it last time. We got radical 2 over a, I believe. I think that's right. Remember, we took the integral over, we squared it and took the integral over 0 to a, and we set it equal to 1, and so we solved for this thing in the beginning. Because the point is that anytime you write a wave function, it has to be, maybe this is only for the first, whatever. Anytime you write a wave function, it has to be normalized, meaning if you take the integral over all space squared, it has to be 1. That means it's the problem, because the squared integral is the probability of finding it somewhere. So if you say, what's the probability of finding it in all of space, it better be exactly 1, because that's what probability means. Of course, now then you can do the other problems which are not on the homework, so you might need to do them, but it would just be, what's the probability of finding something at another location? They would always tell you a range, and you would just square the wave function of whatever state you're in and integrate in that region. So that's the same thing. If we had this state and we set n equal to 1, and we said, what's the probability of finding it on the right quarter of the infinite well, we would just square that function, integrate it from, 3/4 a to a or whatever, and you get a number. It probably would be like, I don't know, not very much. It wouldn't be a quarter, probably, because it definitely wouldn't be a quarter, because it's not an evenly distributed function, but it's like, be like an eighth or something. Anyway. So this hopefully is a little preview of what you will see. I hope this was not a waste of time. The point is that there's quantum numbers. That's the main point I want to say. The point of quantum mechanics is that when you solve this differential equation and you impose the normalization condition and the boundary conditions of systems, you get allowed values, and they're called quantum numbers, and they look really weird, and sometimes they do weird things, but they tell you the allowed states, and that's all you care about. You don't care about the states in between, you don't care about the potential in any other aspect, you only care about the allowed energies, because those are the only things that really sort of exist in some sense. Okay, I'll stop. All right. Now, what problem was that?
I don't think that was.
Okay.
Oh, sure.
Kind of took the reins on that one and just went with it.
I did a lap.
You did a couple.
Yeah, I came back.
I don't know. Do you have questions?
I went to the 3 I needed.
What were the other questions about?
That was all of them.
Well,
Oh, and okay.
245.
Did you look at next, it was the homework doc?
Yeah, he posted it at the beginning of this.
Is it chapter, or is it the next chapter?
10.
Okay, good, because I think this is in 10. Actually, can I look real quick? Oh. Okay, yeah, so, okay, here we go. Here's some nice pictures.
Yeah, those are, I noticed those.
These are the D state, so that's the whatever L
They're
equals
orbitals.
whatever. Yeah, orbitals.
No.
They're both, yeah.
Oh, good. Okay, so 10. So this is for the audience at home. Equation 10.11 is the three-dimensional square well. So you can see the three quantum numbers. They actually do it for not a cube, but for a prism where the dimensions are different. So that's fine. It looks, well, you can see how it looks. It's pretty. Oh, that's a quantum dot. Oh, I never knew that. Oh, okay. That's what a quantum dot is.
Oh, the diode, right? Was that the diode thing?
I don't know. You lost me.
Okay.
I know what a diode is roughly. Oh, yes. No, that was the scanning tunneling microscope.
Oh, that, okay.
Okay.
Cool. Oh, okay. Wow, this is like what I just talked about. Okay, good. So let me just go over real quick what for everything I said to what is in the book, which is the same, but they call it something else. So, yeah. So on page 180, the quantum dots thing apparently, which I never heard, I literally have never heard that before until last night. But the quantum dots thing is the thing where you do the infinite square well in 3 dimensions, but of course you could make them, instead of making it on a cube like I did when I drew it, you could make them all different dimensions. And you end up getting that if this is the x part and you have ax, let me call it L for now, for the length. The length in the x direction, this is the x component, but you would have to add, so it should be nx squared and then over Lx squared plus ny squared over Ly squared plus nz squared times pi squared h bar squared over 2n, whatever. It's the same as this, but you have 3 separate. And the reason you get that is because of you solve the same equation, this, 3 times, you get 3 separate sine functions, like 3 separate size, right? And the true wave function is the product of them. You multiply them together. So whatever. But then you get 3 different size, and each of them has its own. So you'll have a sine kx. Sorry, k sine k sub x x, and you'll have to set this will have its own boundary conditions equals 0, and so you'll get k. Oh, sorry, equals. That will okay. Psi x will be this, and then you'll have y and z. The boundary condition will be psi of x at Lx, which is the end of the x component of the box, right? Is sine of kx times Lx, and of course this has to be 0 because it's an infinite well again. Then you'll get kx Lx equals nx pi. That's the quantization condition, and you get exactly the same thing for y and z, and that's how you get this. It's the same exact derivation, but I just want to show you that it quantizes in 3 dimensions at the same time, and therefore you'll get the energy is just the quantization of each one, just like this, but separate, and you'll just add them all together because, yeah, add them all together because if you plug that function in where they're multiplied, times sine kyy times sine kzz, if you plug that in and you do it, you'll just solve for the energies. So again, I just want to make sure you know that this is not something, even though I've been using it over and over again and I've memorized it, you don't need to memorize it. You can absolutely get it by if you know the wave function, it just literally is E. So just plug it in and find E. But you can memorize it if you want. Okay, is there any questions? So hopefully that's like enough for next week's homework.
You're not going to be here Saturday?
No, I will not be here Saturday.
Same.
Oh, I'm sorry. I was going to ask. Yeah. So sorry. Okay. So this Saturday, I'll be in New York for a event. It's like anyway, we're going to a
For
play.
your life.
For my life, yes. Come From Away. Have you ever heard of Come From Away?
That sounds familiar.
It's like on Broadway play. It's about after like 9/11, like there's one airport in Canada, like accepted a bunch of American flights, and something
I
happened
didn't
there. I
realize
guess
there
they
was
all
like a...
there's a Broadway play, a Canadian play.
Ooh.
So my expectations are
Okay.
low, but
See, I sold you on that joke. You just sold me on that.
I have a lot of Canadian friends, so I always make fun of them. But